Welcome back to the Thermodynamics series. In this video, we will look at the application of the first law, energy transfer and heat capacity. Let's get started. The first law of thermodynamics states, while energy can be changed from one form to another, the total energy of the universe is constant. In other words, any energy that is lost or gained must go somewhere or come from somewhere. Energy cannot be created or destroyed. When working with energy chains in your system, the first law provides a formula for us to work with. The energy chains of your system must be equal to the energy transferred across its boundaries from the surroundings. There are three ways in which energy can be transferred: heat, work, and mass flow. The dots tell us that it's mass per time or moles per time. Then the equation becomes the change in energy of the system is equal to heat plus work plus mass flow. First, we must look at the forms of energy: kinetic energy, potential energy, and internal energy. Kinetic energy is the energy associated with bulk motion of the system. Potential energy is the energy associated with the bulk position of the system in a potential field, and internal energy, which is the energy associated with motion, position, and chemical bonding of the individual molecules within the system. Thus, our equation becomes internal energy plus potential energy plus kinetic energy equals heat plus work plus mass flow. Remember that kinetic and potential energy are for macroscopic motion or relative position, say if your system moves or changes position, and internal energy is the molecular motion or relative position if the molecules in your system moves or change position. If your system doesn't move or change position, we simplify our equation to change in internal energy equals heat plus work plus mass flow. And of course, only open systems have mass flow, so we can simplify our equation more for closed systems. Change in internal energy equals heat plus work. Let's look at ways in which internal energy of our system can change: changes in temperature, changes in phase, and changes in chemical structure. When working with an ideal gas, we can in some cases simplify our equation more. Since an ideal gas do not have intermolecular forces, its internal energy only depends on motion, and temperature affects motion. Thus, if temperature is constant, the internal energy will not change. This provides another formula: heat equals negative work. Before we look at the different elements, we first need to look at reversible and irreversible processes. A process is reversible if after the process occurs, the system can be returned to its original state without any net effect on the surroundings. A real-life process can never be reversible. It is just an idealization to help with calculations. If a question uses the words maximum efficiency, you know that you can base your calculations on a reversible process. Then, to get the real values for work or heat, you can just multiply or divide with the efficiency percentage. To know when to divide or multiply, you can remember this. If your process is a compression process, work is put into the system. To make this process efficient, we would want to do the least amount of work. If we know our system is not 100% efficient, we would have to divide with the efficiency percentage, making the work more and thus less efficient. The opposite is true for expansion. If we want our system to expand, our system does work. Thus, we get work out of our process. If our process is 100% efficient, we would get the most work. Thus, if our system is not efficient, we should multiply our work with the efficiency percentage, making the work less and thus less efficient. In real life, we have irreversible processes because real-life processes have friction. The work obtained is always less and the work needed is always more. Now, let's talk about work. Consider a piston cylinder assembly of an expansion process. When a force causes displacement of a system boundary, we call it work. The displacement can be seen in our assembly since the volume of our system change, and the force on the system boundary is just the pressure. Thus, if we look at our PV diagram, the area under the curve would give us the work. When a process is reversible, we can calculate the work with the following formula. Integration is technically just area under a curve, which makes sense. When we use this integration formula, we usually have a pressure change and can't just plug in one of the values. Thus, we need to replace P with the ideal gas law. We can use PV equals RT, which we rewrite in terms of pressure and just plug it in. Or if temperature is constant, we can use PV equals PV, which we can also rewrite and plug into the formula. Remember that you can only use this formula when it is stated that the process is reversible and it is an ideal gas. And lastly, if your process is irreversible, you can calculate the work if the external pressure stays constant. Then we get shaft work. Shaft work refers to the energy transferred from or to a system through a rotating shaft, often as a part of a mechanical process involving machinery like turbines, compressors, or engines. Flow work is the work the inlet fluid has to do to displace the fluid that is already within the system so that it can enter the system. If work is done on the system, the work is positive, and if work is done by the system, the work is negative. Let's do an example where we calculate the work in a system. Consider an isothermal expansion of a system that contains 1 mole of gas at 2 bar within a volume of 10 liters. The gas in the cylinder expands until the pressure of the gas matches the pressure of the surroundings. The final volume is 15.2 liters. Calculate the work done by the system during this process. We know atmospheric pressure to be 1 bar, thus we know the external pressure and the final pressure of the system. We can use our irreversible process formula to calculate the work. We plug in our values and find the work to be minus 520 joules. Since work is done by the system, we can see that the work is negative. Now, let's rephrase the question. Consider the isothermal expansion of 1 mole gas from 2 bar and 10 liters to 1 bar and 15.2 liters. Calculate the maximum work done by the system. Since they ask for the maximum work, we know that it is a reversible process and we can use the reversible formula. And since this is an isothermal process, we can replace the pressure with PV over V. So we plug in our values and get an answer of minus 636.4 joules. And once again, we can see that the work is negative, indicating an expansion process. Then they ask, if the efficiency of the system is 81.7%, what is the real work? Since this is an expansion process, we need to multiply with the percentage. We plug in our values and get a negative work of 520 joules. Now let's consider heat as a transfer of energy. Heat is the transfer of energy between the surroundings and the system, where the driving force is provided by a temperature gradient. Also recall that in an adiabatic process, there is no heat flow. Heat from the system to the surroundings is negative, and heat from the surroundings to the system is positive. There are 3 ways of heat transfer: convection, radiation, and conduction. Convection is when heat is transferred through fluid flow. Radiation is the transfer of heat through light. And lastly, conduction. Conduction is the transfer of heat through a material without any movement of the material itself. Heat flows from hotter to cooler areas by transferring energy between particles, especially in solids where particles are tightly packed. From this, we get an extra formula. Internal energy is equal to heat capacity times mass times change in temperature. And if there's no work, heat is equal to heat capacity times mass times change in temperature. Let's do an example. A steel cup with mass of 200 grams, initially at room temperature, is filled with hot tea weighing 0.6 kilograms. The tea is initially at its boiling point, 100 degrees Celsius. After some time, thermal equilibrium is reached. The specific heat capacities for steel and tea are constant and 490 and 4180 joules per kilogram Kelvin respectively. Assume that the cup and the tea are isolated from the surroundings. Calculate the temperature at equilibrium. This example brings another topic, equilibrium. Equilibrium refers to a condition in which a state neither changes with time nor tends to spontaneously change. There is no net driving force for change. There are a few types of equilibrium: mechanical, chemical, thermal, and phase equilibrium. Mechanical equilibrium is when there is no pressure difference. Thermal equilibrium is when there is no temperature difference. And chemical and phase equilibrium is when there is no tendency for a species to change phase or chemically react. Let's look at the question again. We are given the mass, heat capacity, and initial temperature of the cup and tea. Since thermal equilibrium is reached, we know that at the end, the temperature of the cup and the tea will be the same. We also know from the first law of thermodynamics that if energy or heat is gained, something else had to lose that energy or heat. Thus, we know that the heat the tea loses is equal to the heat the cup gained. Thus, we can use our conduction formula for no work. We plug in the values for the cup and simplify, as well as for the tea, and then we solve the equations simultaneously and get a final temperature of 103 degrees Celsius. And that's our first few calculations with work and heat. I hope this video helped you understand these concepts better. In the next video, we will look at heat capacity and calculations using the first law, simplifying equations based on our types of processes, and do examples with open and closed systems.